Welcome to lesson 2 of our third unit. So we're going to be looking at solving trigonometric equations algebraically. Our previous lesson looked at solving them graphically. We're kind of moving more into the realm of being able to picture and more kind of fluently answer questions regarding these trigonometric equations by using specific those special values of the unit circle that we learned in Unit 1. So you'll probably want to have your unit circle handy to refer to pretty often. You can use a calculator for some of these examples, but quite a lot of them you don't need them because we do use unit circle values, which are exact values anyways. So we see that right away, right off the hop in our first question here, that we talk about exact values. The second you see that word, you can assume that this is a question that might appear on a non-calculator part of an exam or on a test. When it says using a calculator, obviously, like we see in example 2 here, that's when you can use a calculator. That will be on the calculator section of like the test and the exam. And there will be a calculator section on this test. So just a couple heads up. This is a beefy lesson in terms of the number of examples there are. So I'm leaning towards breaking it into 2. So if you feel like it's ended and there's still more examples to do, just go into the next video and that's where you'll find them. Because I don't want to have it just be so long that, and then you have to like remember like how far into the video you were. I just would rather break it into 2 pieces. So we'll look at example 1 to start. So it says solve each of the following trigonometric equations using exact values. So again, that is implying that we're talking about, that's a very fat pen, the unit circle. Values and special angles. So when we see sine theta equals 1/2, we need to keep a couple things in mind. First thing is that according to all students take calculus, sine is positive in quadrants 1 and 2. So we're going to have 2 answers potentially. So sine is positive in 1 and 2, so I expect an answer for quadrant 1, and I expect an answer for quadrant 2. The other thing I need to consider is, okay, well, when in quadrant 1 does sine theta equal 1/2? And if I have those values memorized, or if I have to look at my unit circle, I'm going to see that that happens at pi over 6. And again, I'm going to use radians because that's the domain that I'm given in my question. Okay, so in quadrant 1, it's pi over 6. That's kind of like my reference angle if you want to think about it that way. And so then in quadrant 2, I'm looking at 5 pi over 6. And again, I get that by taking it away, always measuring from that horizontal axis. So if this is pi, well, that's the same as 6 pi over 6. And I'm taking away that reference angle, so taking away 1 pi. So that's how I get that. In our second part of this example, same idea. So I look and all students take calculus. This is a positive value, so I'm looking at quadrants 1 and quadrants 3. My reference angle is going to be when tan theta equals the square root of 3 in quadrant 1. So if I have to think back on that, it's going to be at pi over 3 that happens. And again, the more you memorize your unit circle, the faster you'll get at this. I always go back to that table that I created a video for on like how one way to remember how to all these different values. But whatever kind of memorizing strategy you use, great. As long as you can come up with this value, because then that allows me to come up with my theta for quadrant 1 is pi over 3, and my theta for quadrant 3 is going to be 4 pi over 3. And again, measuring from pi, but in this case, measuring in this direction. So adding an extra pi over 3 to pi. When I'm doing it with a calculator, it's kind of nice and easy in the sense that we need to like just consider what does the calculator spit out. But we do still need to keep in mind that we should always have two solutions unless my domain is very restricted. But again, I'm working in radians, so I would need my calculator in radians. Okay, and again for A, where it says sine theta equals 0.81, I'm working in quadrants 1 and 2. So I will still expect two answers. I'm going to figure out my reference angle first, and then I'm going to go from there. I get 0.94416, I believe. So that rounds to 2. Just double check. Yeah. And so that's in radians. So then I'm going to take this value and subtract it from pi to get my quadrant 2 answer. In general, I can say theta 1 is 0.9442 because again, your reference angle is always that angle in the first quadrant. And theta 2 would be pi minus theta r. So that's going to be, I'm going to do that on my calculator if it decides to work for me. Drag it over here so you can see. I'm going to go pi, subtract, and what I like about this calculator is that it lets me actually just type in the answer from the previous line, and so then I get 2.1974. So both of those are solutions, so I would box them both. Okay, so that's kind of where it becomes a little bit trickier maybe with a calculator, is that you just need to bear in mind that the calculator is only going to give you one answer, but you need to still do your person thing and use your brain to know that you should still have more than one solution. Same thing happens here. All students take calculus. Because tan is negative, my value for tan theta is negative, I'm going to expect to have two solutions, but in quadrants 2 and 4 this time. So I can still do a reference angle, in which case I would do, I'm going to type in tan inverse of, and I'm just going to take the positive value. I'm going to ignore that negative completely. I'm going to see what that gives me. So again, tan inverse of 1.45. And that gives me a reference angle in radians. And again, you can always check by going into mode if you're using a graphing calculator. Check that it's in radians. If you're using a regular calculator, it should say somewhere up along the top of your screen rad to make sure you're in radians. So 0.9670 is my reference angle. So my angle in quadrant 2 would be pi minus my reference angle. So again, I can do that nicely on this calculator because it has that option to use the answer button. You can see that kind of in blue. Your calculator, if you're using any sort of scientific calculator, should have that option somewhere on there as well, so that you don't have to worry about typing things in. And that gets you 2.1745. And again, we don't need to write rads after. It's kind of the nice thing about radians is that we don't need to include those units. For quadrant 4, I would go 2 pi minus my reference angle because I'm measuring from here, which is 2 pi, measuring backwards, counterclockwise, in which case I would get 2 pi. And then in this case, I'm going to have to go back to that previous line, 0.9670. and that would get me 5.3162. That's my other solution. Okay, when they don't tell you to have a specific number of decimal places, going to like 4 or 5 decimal places is not a bad idea. So just bear that in mind. That's why I'm keeping so many decimal places here. In example 3, it says solve the trigonometric equation using exact values on the interval 0 to 360. So exact values tells me I'm not using my calculator, but this time my answer should be in degrees because that's what my domain is given in. So when I look at this, I see 1 over root 3. I automatically start thinking about all students take calculus, and tan is positive in 1 and 3. So that's where I can expect my 2 answers to be. My reference angle is, I'm in the habit personally of thinking about it in terms of radians, so I automatically think of it as pi over 6, but then I have to mentally work backwards and be like, no, I need to put my answer in degrees, so that needs to be 30 degrees. And again, I'm pulling this from my unit circle. So have your unit circle out because you might be a little bit rusty on this because we didn't use it in our previous unit. It was all the way back in like February that you did this. So we've got, that's our reference angle. So in quadrant 1, that would be 30 degrees, but in quadrant 3, that would be 180 plus an additional 30 measuring this direction. So that would be 210 degrees, and those would be my 2 answers. Okay, so this is basically how the whole lesson is going to go for all of lesson 2. So feel free to at any point pause it, try things on your own. Things are going to get more complicated once we hit example 5 though. So example 4 says solve the following trigonometric equation using a calculator. So again, anytime we see decimal places really over here, it's going to be kind of a mental cue. Okay, maybe I'm using my calculator. But again, I'm working in degrees. So in this case, the first thing I'm going to do before I do anything else is I'm going to go into my calculator. And again, depending on your calculator, it has to do, you do this a little bit differently, but I'm going to switch it into that degrees mode. Then I look back and I'm like, okay, sine is negative 0.38. Sine is negative in quadrants 3 and 4. And to find my reference angle, I'm going to do the sine inverse of just 0.38, ignoring that negative, because that puts it in quadrant 1. And so automatically when I get that, I get 22.3337 degrees. Okay, and that's my reference angle. Theta 3 in quadrant 3 is going to be 180 plus that, so 202.3337 degrees. And in 4, it's going to be 360, subtract that, which would be 337.6663 degrees. And if you have to use your calculator for that, double check my math, my mental math, to see if that's right. I'm going to do that, actually. 360 minus 3 equals, yes, perfect. Just working with those long decimals kind of throws me for a loop. Okay, so up to this point, we have strictly worked with single trig functions in an equation. In example 5, we're still seeing the same wording. We're solving trigonometric equations. We are using exact values, and we're back in radians. So we don't need to use our calculator. We don't need to worry about switching in radians, but we need to mentally switch into radians. Here, it's a matter of you can treat it as a variable. So if we said, let sine theta equal x, and then you rewrite it as 5x plus 2 equals 1 plus 3x, this might look a little bit more manageable for you. This is a perfectly viable strategy for solving any equation that gets more complex than the previous ones when it comes to solving trig equations. So from here, we look at collecting like terms. So we've got 2 like terms here on opposite sides of the equal sign, so I'd move the 3 over, so that gives me 2x, because I'd be subtracting. And then I've got my 2 like terms here, 2 and 1. I'm going to move them onto the right side. So equals subtract 2, so that gets me -1. X equals -1/2. Okay, but I'm not done here because I wasn't solving for x. That was not the original purpose of my question. I need to go back and plug this piece back in. So I'm going to go back, and that needs to be substituted back in. So instead, I'm going to see that showing up as sine theta equals -1/2. Okay, so kind of plugging in that piece. So x appeared in lieu of sine to start with, and so then we have to work back and plug that sine back in, because my ultimate goal is to solve for theta, not for x. And so theta as a reference, when sine is 1/2, would be pi over 6, and that's what we saw before. Okay, but because it's negative, that means I'm dealing with quadrants 3 and 4. So I'm going to work again in quadrants. 3 would be 7 pi over 6, and quadrant 4 would be 2 pi minus pi over 6, or 11 pi over 6. And again, we're calculating these by going pi plus pi over 6 and 2 pi minus pi over 6. Okay. If you didn't want to do that, if you wanted to just work through this question as if it was as it's written, you are more than welcome to do that. How that would look is I would literally do the same process. I would just miss that one step where I need to like plug sine theta back in. This honestly would be the way that I would prefer to do it, but this strategy is a really good strategy, especially once we get to some later examples. And some people just get overwhelmed seeing so much language and letters and symbols thrown into our equations, and it can jumble them up sometimes. So this is a perfectly viable solution. I probably would have just gone straight to the part where I'm identifying like terms and writing 2 sine theta equals -1. So sine theta equals -1/2. And I would end up in the same place as I had right here. Okay, it just gets there a little faster. If you choose to do this method, the key thing is that you must write this statement. Otherwise, all of a sudden, you've introduced a new variable into the equation with no explanation of what it means or what it represents, and that costs you marks, and it just is confusing to an outsider who's trying to read your work. So that statement must happen in order to use this strategy. Okay. So B. Same thing goes here. You are totally welcome to use that strategy. I'm not going to use it this time. I'm just going to work straight from here. So, you know what, I'll use highlighters this time. I like it a little better. Okay, so I'm going to look at my cos terms, and they get me 3, and I'm going to subtract 1 from the other side of the equal sign. So it's 2 cos theta. And I'm going to identify these as like terms on opposite sides of the equal sign as well. So I'm going to add this 1 onto the other side, so that gives me positive 2. From here, divide by 2 on both sides to isolate cos theta equals 1, and that's a more manageable equation. At this point, it looks a lot like what we saw in examples 1, 2, 3, and 4. So this is more manageable. Now I can start thinking about my unit circle. Now, 1 as a whole number is a very special value on our unit circle. And so if we think back to what it means, cos theta is our x value on our unit circle. So when x is positive 1, and that we only see in very specific circumstances. So we don't even need a reference angle. We don't even need to think about when is cosine positive, because specifically positive 1. So we need to double check our domain. We're inclusive of 0 and of 2 pi based on the fact that they're using square brackets here. And cos is our x value. So x is positive 1 here on our unit circle, which is both 0 and 2 pi. So I will list both as options. Again, I can list them both as options because of these square brackets on our domain in the question. Both are included. If, for example, we had a rounded bracket here, then I would not include the 2 pi as a possible solution. But as it stands, it is included. There's a square bracket, so I can. Example 6, if you want to give it a shot at this point, I would really recommend pausing the video. Just a couple of key things to watch out for is that we're still talking about exact values. That means we're not using a calculator. But in this case, we are working in degrees instead of radians. So make sure you switch your brain into that mode. If you ever need to like double check, just always go back to the question and say, what were my kind of restrictions on what numbers I can put for theta? What units were they given in? Because that tells you the units that you're supposed to answer in also. So pause the video, give these two a shot. They look a little complicated. If you want to use that substitution idea of saying let x equal tan theta and solving for x, isolating x and then putting tan back in, just don't forget to put tan back in. I'm going to solve the first one without using that strategy, but the second one here, now that I'm adding a radical in there, it looks pretty intimidating to me. So I will use that substitution strategy here. So you'll see the difference in my answers. But yeah, give it a shot on your own first. Okay, so again, collecting like terms and moving all my tans onto the left, all my constants onto the right, I get this equation. But tan theta only equals 0 when sine theta equals 0, because tan is actually sine divided by cosine. Okay, and again, we talked about this briefly in Unit 1. This is going to come up a lot. This identity, this relationship is going to come up a lot as we continue through this unit. So it's a good idea to start thinking about tan as a ratio of sine divided by cosine. And it can't be when cosine equals 0 because we're not allowed to have a 0 denominator. That's why we saw that those tan graphs got asymptotes in them. So only when sine theta equals 0 does tan theta equal 0. And sine theta, if we think about it in terms of our unit circle, is our y value. So when y equals 0 happens at these 2 points, 0, 180, and 360. And again, I'm talking in degrees because that was what I was told to do in the question. Because of those square brackets again, it's all inclusive, 0 and 360. So I can list all 3 angles in this case. So again, feel free to pause the video. I'm going to do that substitution piece for this equation. So my first statement would be let x equal sine theta, and I'm going to go from there. But feel free to pause and try it on your own. So I didn't finish solving, but just so that we kind of pause to reaffirm, since I've said let x equal sine theta, I put x in place of sine in both locations. So then I'm going to try and collect my x terms. In this case, I move them onto the right-hand side just because I didn't feel like moving the square root of 3. It had nothing else to combine with anyways. and then I had to divide by that -2 that I had left over. So I just throw the negative out in front and then work with the ratio otherwise. It's just a personal preference because it lets me think about my reference angles a little bit easier. Because when I talk about my reference angle, I'm looking in quadrant 1. Well, now I'm just talking about √3/2. And I know that that is actually 60 degrees, or if you were kind of landing on radians first, you were thinking pi/3, but again, we have to talk in degrees because of the domain that we're given in the question. So that's my reference angle, but we know that sine is negative in quadrants 3 and 4, as we've come across multiple times already in these examples. And so I'm going to work in quadrant 3. It would be 180 plus 60, which is, 240. And then in quadrant 4, it would be 360 minus 60, or 300 degrees. And so that would be my final solution. But again, the key thing to remember is we have to write this statement. This statement is incredibly important, and we need to remember to sub back in. Those are two pieces that we need to remember if we're using this method of substituting x in for sine or any other trig function. So I'm going to stop here. Our next example gets into quadratic equations with trig functions. So this video will stop here, and the next video will pick up on example 7.